In this example, we are given 4 different circuits. Each one of them is a single loop circuit, and they have different sources. Sometimes it's a voltage source, sometimes it's a current source, and they're all connected to resistors. And they defined I and V in each one of the circuits with the polarity and the direction, and we're asked to compute the value of the current I and the value of the voltage across that resistor, and then the power dissipated in each one of these resistors. So let's get going and figure out how we can solve these exercises. So we'll focus on the first one in here. Again, usually we focus on the resistor, or in this particular case, we're asked to compute the power associated with the resistor. So I'll just focus on the resistor and figure out the current and the voltage across a particular resistor. So in here, what I have in this particular diagram, I have the following. I have a current source in here, and that current source is generating this particular current. So I, in this particular case, must be 2 amps because it is the same direction. It's coming out of the current source, and I know that the current provided by a current source is stable no matter what the voltage across it is, and it's 2 amps. And because there's no other elements going between that particular source and this particular resistor in here, that means this particular I is exactly the same as the 2 amp. So that's straightforward. What about the voltage? Well, we don't know the voltage across a current source, so we have to compute it. And because we have a resistor that we know its value and we have the current going through it, so it's a straightforward implementation of Ohm's law. So Ohm's law tells me in this particular case, V equals I times R. But obviously I had to figure out the passive sign convention is correct. So the I is hitting the positive first. In this particular case, the positive of the resistor. That means I should use positive. So it's as straightforward as saying, well, I is simply 2 amps and times 5 ohms. That means it is just simply 10 volts. All right, what about the power associated with this resistor? Well, or consumed by this resistor, there are multiple ways to compute it. We can either compute it using one of the rules that we have, or I times V. You choose. I'll choose I times V in this particular case, and passive sign convention tells me the current is hitting the positive, so it must be positive in here. So it's simply 2 times 10, which is simply 20 watts. So this is for this particular circuit in here. All right, moving on to the next one in here. So we move on to this particular circuit. So again, I will focus just on the resistor in this particular case. So I'll highlight it in here. And again, we're asked to compute the power, the I and the V. In this particular case, I have a current source and a resistor, and the current source is generating current that is going this particular way, and its value is 3 amps. So technically it's going here and it's going through this particular resistor and coming back in here, or we can think about it as like it comes back in here as a 3 amp. So I have a 3 amp coming in here. And this particular direction of I is opposite to the current source. So it's straightforward implementation. We can say, well, I is just simply negative 3 amps. That's what we can say. It is the same current, it's just in the opposite direction, so it's negative 3 amps. Okay, how about the voltage? Well, we don't know the voltage across this current source, so what we need to do is we need to focus on the resistor, and based on the value of Ohm's law, which is V equals IR, I can figure out what the voltage is. But before I continue, I need to make sure the passive sign convention is correct. So the I in this particular case is hitting the positive, so positive is okay. All right, so we go in here, so the value of the voltage is simply positive, and then there's a negative 3 because this is the value. This negative is coming from the value of the current in here. This negative, I know that this is coming here. It's not from passive sign convention, it's from the value of the current. All right, so times R, and that R is just simply 15. So what I have in here is negative 45 volts. That's the value of the voltage across this particular resistor. Of course, we can compute the power. The power is simply P equals, and I can use IV or I squared divided by R, or I squared R, or V squared divided by R. It's up to you. I'll use I and V so that I can show you passive sign convention and the different signs. So in this particular case, passive sign convention tells me I times V. Well, I is here hitting the positive. So what I have to do is I have to do positive I times V, and in this particular case it's positive. Well, I happen to be negative 3 and V happen to be negative 45, so I just substitute these two values and I'll figure out that number in a second, which is 135 amps, or watts, sorry, not amps. We're computing power, so it's 135 watts. Okay, I encourage you to use the P equals I squared R or V squared divided by R, and you should get the same exact answers. All right, we'll move on to the next circuit, this one here. So for this particular circuit, we are given, in this particular case, we have a voltage source instead of a current source and a resistor. And we're asked to compute the I and the V. And again, I'll just highlight it just to emphasize that this is what we're looking at for now. All right, so what do we have? Well, do we have the current in here? We don't have the current. As opposed to the previous two examples or two circuits, what we have is the voltage. So I don't know anything about the current going into it or out of it. Okay, I don't even know its direction. What I know is the voltage. So if the voltage in here, that means I have this one. Let me just highlight in here. This is positive, this is negative, and it's the top one is 5 volts higher. And if you actually move in here, you'll see that the voltage I'm looking for is in the exact complete polarity. So what I have is I have V is simply negative 5 volts because it is the same voltage in terms of value. It's just because I put negative in here and put positive in here, which is the opposite to what I have as a voltage source. It's just simply negative 5 volts. All right. Now that we have the voltage across a resistor and the value of that resistor, in this particular case, we're given the value of the conductance instead of a resistance. All we have to do is take its reciprocal. So if I need the R, I just need it to say R is simply 1 divided by G, which is 1 divided by 0.2 Siemens, okay, which is simply 5 ohms. Let me just write it in here. Okay. So simply, it's just simply 5 ohms. All right, now we can go on. Well, V equals I times R. Do I have the voltage? Yes, I do. So this time what I'm looking for is actually the current. So I is simply V divided by R. But before I continue, I need to make sure the passive sign convention applies. So I have I, and in this particular case, it's hitting the negative. So what I need to do is I need to put a negative in here, and I put the negative in here. All right, we continue, and we say, well, it's negative 5 volts. Divided by R, which is 5. So again, let me just emphasize, this first negative is coming from the passive sign convention. The second negative in here is coming from the fact that the voltage is actually negative in here. So we have two negatives. So what do we get? We get that this particular value is 1 amps. So the current is 1 amp. Now we can compute the power associated with this resistor. It's simply I squared R, or we can keep using I times V. It's up to you. You can use both. You should get the same answer. So I times V. But in this particular case, the current is hitting the negative first. So what I need to do is I need to say, well, this should be negative. All right, so I have negative. I is 1, and the V is simply negative 5. And this here is 5 watts. That's how much power is being consumed by this particular resistor in here. All right. Moving on to the last circuit. So in this particular circuit, we're also given a voltage source. And in this particular case, the voltage source is in the same polarity as the V. So I have a positive in here and I have a negative in here. So it's straightforward saying V in this particular case is 10 volts. Okay, what about the current? Well, current V equals I times R. But again, I'm going to just focus in here just so that I can see what passive sign convention. Passive sign convention tells me the current is leaving the positive. But this isn't what I'm looking for. Well, I know if it's leaving the positive, it's going to come back in here. So if it's coming back in here, that means it's hitting the negative. That means I have to use negative in here. All right, now we can go on. This is what we're looking for. We're looking for the I because I know the value of V and I know the value of R. So I is simply negative V divided by R. And in this particular case, it's negative 10 divided by 5. Of course, this is 5 kilo ohms. So I is simply negative 2 milliamps because 5 is in kilo ohms. Okay, so negative 2 milliamps. So that tells me that the current is technically going that way, but we're going to stick with that assumption so that we don't get confused. If you just got a negative value for I or V, whatnot, just stick with it, keep it, and just whenever you use I or V, just substitute it with a value along with its sign. So to compute the power in this particular case, P equals I times V, and we have seen that passive sign convention tells me, well, the current is going that way, so it's hitting the negative first, so I have to put negative in here. So that tells me it's negative times negative 2 milliamps times the voltage happened to be 10, and that simply tells me that it is 20 milliwatts. It's 20 milliwatts because the current in here is actually in milliamps. So pay attention to the units.